Hi, I'm Eleni Forster.
I'm Julia Mulders.
And I'm Miguel Rodriguez.
We focused on the region of Europe and the British Isles, and we took a geologic approach to surface exposure dating, aquatic fauna, and historical documentation. Surface exposure dating is a collection of geochronicles techniques in which science of determining how old a rock, fossil, or sediments are by using the indications inherent in the rocks themselves. Scientists use dating tools for estimating the length of time that a rock has been exposed at or near the Earth's surface. Surface exposure dating is also used to date glacial increases and decreases, lava flows, erosion history, rock slides, meteorite impacts, cave development, fault scarps, and other geological events. It is most useful for rocks which have been exposed for between 10 and 30 million years. The age of shear formation at the Laxford can be established by radiometric dating of the granite intrusions that we can see to the picture on the right. These have yielded ages of 18,055 years. However, the gray genesis are much, much older. In northwest Scotland, while these rocks were still in the middle crust, subsequently these units were uplifted too close to the Earth's surface so that they were overlain by the Toroidean strata some 1.2 billion years ago. Next slide. The most common types of surface dating are radionuclide dating and lycanthropy. Radionuclide dating is one of the most common techniques, and it is because Earth is being constantly bombarded with primary cosmic rays, which are high energy charged particles. When the high energy charged particle reaches the atmosphere, it changes the energy in the different events. Lycanthropy represents a very useful dating technique in Europe and the British Isles, and lycanthropy is utilized for rock surfaces less than approximately 10,000 years old. Lycanthropy is most useful for rocks that have a specific rock surface that is plentiful, and every now and then is the solely correct technique for estimating the age of a rock. Next slide. In the future, with the help of different exposure dating the dating techniques mentioned, I believe that there will be an influx in synthetic carbon found in the makeup of rocks themselves. We will probably discover different technologies to date rocks and even be able to recreate in real life the climate of the Earth at that exact moment in each layer of the rock uncovered. With the use of geological tools and different techniques, along with historians, archaeologists, and anthropologists, we do see a clear picture of our planet Earth. While dating rocks, we also see the different fossils within the layers and the minerals that make them up.
Aquatic fauna are freshwater fossils that include teeth, bones, trace fossils, sedimentary layers, etc. These fossils have led to an abundance of interesting discoveries. The Panaeosaurus is the first freshwater species known, and it was found in a coal mine in Hungary and 84 million years old. This creature belongs to a family of ancient aquatic reptiles known as mosasaurs, which look like a cross between crocodiles and whales. It was found amongst thousands of fossils that range from 3 feet, 1 meter, to 13 feet, 4 meters. It was most likely a true freshwater dweller and not just a marine mosasaur, as all of the fossils were found in one location. This location was part of a chain of tropical islands situated in the middle of a massive freshwater seaway that separated Africa and southern Europe. Because of its massive size, it was most likely the crown predator of these waters, but it wasn't very threatening because of its small and sharp teeth. And then trace fossils are tracks, trails, burrows, or other markings left behind by organisms. Zoophycos are a type of aquatic trace fossil. They are a three-dimensional trace with a central vertical shaft and lateral feeding traces with spiraling layers. The fossil is usually found dispersed throughout pretty deep water and marine turpidite beds. Turpidite is a sedimentary bed deposited by turpidite current and turpidite flow. The fossil can also be found in a range of water depths, including shallow water with low oxygen levels. And the Lagonatus Lagan Anecta's Rich Terre, which translates to Laguna swimmer, is a 132-million-year-old fossilized sea monster that was excavated in 1964 in a clay pit in Starstadt, Germany. But it wasn't until 2017 that it was studied by international scientists. It was an 8-meter-long skeleton of a plesiosaur, which was a long-necked aquatic reptile that resembled the infamous Loch Ness Monster. The remains found were most of the skull with long fanged teeth, as well as vertebrae, ribs, and bones from its forelimbs. Scientists found that its upper jaw may have had nerves that were connected to electroreceptors outside of its snout that would have been extremely useful when searching for prey. It most likely died from a long-term disease based on evidence of a chronic bacterial infection. Next slide. Aquatic fauna are a paleoproxy record because they have physical properties such as composition, texture, soil bed structure, color, density, etc. Scientists can use these properties as well as carbon content to identify the age of these fossils and the changing ecosystems and environments surrounding them. Aquatic fossils can help us understand climate history by telling us what specific temperatures, sea level, and moisture conditions help these organisms to survive. We can also gain an understanding of the current climate by the sediment that these fossils are preserved in. The amount of the fossils over time can tell us whether a change in the environment or climate was gradual or abrupt. Next slide. The future implications that we can gather of climate change will be devastating to freshwater ecosystems unless we take action now. The ecosystems will be impacted physically and chemically and at abrupt speeds. Climate change results in air temperatures rising and heating up these bodies of water. The water level will in turn decline, especially during summer droughts. If there continues to be a lack of rainfall, these ecosystems will eventually dry up and there will be no aquatic organisms left. But luckily, our freshwater ecosystems can be protected by a number of measures. This includes reducing extraction of water from ground and surface water, maintaining water flows and management of microphytes, artificial oxygenation and mixing, etc., so that freshwater ecosystems are not affected by small climate-induced changes. If we also commit to being more environmentally friendly and enforce that corporations reduce their carbon emissions, we can live longer and healthier lives and keep our planet sustainable for future generations.
Moving on to historical documentation. Historical documentation is any document used in the reconstruction of past or historical climates. Historical documents include annals, chronicles, memorial books, memoirs, daily weather observation, private correspondence, illustrated broadsheets, newspapers, journals, pictorial evidence, stall keepers, market songs, early scientific papers, epigraphic sources, early instrumental meteorological observations, books of account, reports on weather damage related to claims for tax, official letters, and sea log books. Historical documentation is used in conjunction with other paleoproxies, such as dendrochronology and ice cores. As you can see on the pictures on the left, these are paintings done in 1565 and 1730 that show winter landscapes. The one on the bottom in particular shows snow in Rome, which is very uncommon nowadays. Rome is very arid, part of the Mediterranean that doesn't get hardly any snow. But in 1730, there was plenty of snow, showing that that's the type of climate that the people of Rome were dealing with at that time period. So the way that scientists use historical documentation is they match this proxy with another dating instrument, and then they make sure that the time series match up, they calibrate it and verify it to reconstruct the data as shown in the formula on the left as well. So two of the most useful paleoproxies, as I stated before, dendrochronology and ice core dating. Both these paleoproxies track annually and seasonally, so they're very accurate at dating the recent past. And Europe has some of the most well-documented evidence, along with both forests and glaciers, to calibrate yearly events. The way that dendrochronology is used in conjunction with historical documentation is by way of tracking the tree rings. Trees respond to their environment And in years with lots of precipitation, they grow faster. In years with less precipitation, they grow slower. So the tree rings reflect years of lower precipitation, thicker rings reflect years of higher precipitation. And the same goes for ice cores. The thicker the layer of ice is, the more it snowed that year. And because scientists can track these annually by looking at the layers, we can match up with what humans were observing in that time period and go back to the layer of either tree ring or ice core. Because of the accuracy of paleoclimatology, we can concur that humans do a great job of observing. Our current historical documents are being created with science in mind, and the trends that we are seeing are alarming. Because of Europe's location in relation to other continents, its latitude, and dense coastal population, changes in temperature could be devastating both if they get warmer and if they get colder. As you can see on the pictures on the right-hand side, the top one shows the extent of the glaciers during the height of the Quaternary Ice Age, and below that shows what Europe would look like if all the ice from the polar ice caps melted. The reason why this is significant is because we are observing massive changes due to anthropogenic climate change. And as stated before, our observations are very accurate at depicting what is happening, and we're already seeing massive changes to our environments around the world due to climate change. This is the bibliography, and we'd like to thank everyone for listening and tuning in.
Thank you for listening.
Thank you.